Here are some properties of limits. Assume that limit of fx when x approaches c and limit of gx when x approaches c exist infinite. Then, for any constant k, limit of k time the function when x approaches c equals to k time the limit of the function when x approaches c. The limit when x approaches c of fx plus gx equals the limit of fx x approaches c plus the limit of gx when x approaches c, which means that the limit of the sum is the sum of the limits. This is also true that the limit of the difference is the difference of the limits. This is also true that the limit of the product of functions is the product of the limits. And also, the limit of the quotient of a function is the quotient of the limits of the functions, provided that the limit of gx when x approaches c is not 0, because we don't want to have 0 in the denominator. If the limit of the function when x approaches c exists infinite, then we can apply the rule that the limit of f times g when x approaches c equals the product of the limits of f with the limit of g, and times for gx equals fx, we are getting the following property. We will get that for any positive number n, the limit of f of x to the n equals the limit of fx to the n. If you look at the left side, we take fx to the power of n and then we take the limit. On the right side, first we take the limit of the function and then we take it to the power of n. Be careful, this is a very confusing limit. The limit of a when x approaches c equals a. This is the limit of the constant function. I can show you the graph. Here is the graph of the function y equals a. You can see that whenever you trace from left to right about x equals c, you always get a. It's the only y value of this function. Also, this is the constant function is traceable from left to right, right to left to any value of x. So we can also apply this as before in the other section that we had, the limit of the function fx when x approaches c is f of c, but f of c is a. For example, limit of 3 when x approaches negative 2 equals 3. Example, let's take the limit of this function when x approaches 2. First, we will use this rule about the constant to get 5 times the limit of this when x approaches 2. Now, this is sine x cubed, so we can use this theorem now to get that. Now I know that sine x is a traceable function. So I can just substitute 2 in the limit. And I get that. As you can see, those properties allows me to find limits of many functions. Example, the limit of e to the power of x plus x when x approaches 6. Now I'm going to use the fact that the limit of the sum is the sum of the limits. And I know that each one of those functions, e to the x and x, are traceable from left to right, right to left to any value of real number x. So I can just go ahead and substitute 6 in the first and 6 in the second. And I get e to the power of 6 plus 6. Let's recall again the 1, 2, 3 theorem. It says that the limit at c exists if and only if 1. The limit of the function from the right of c exists, the limit from the left of x equals c exists, and those limits are the same. We also get from this theorem that the common value of 1 and 2 is L, is the limit of the function when x approaches c. We now like to evaluate limits of piecewise functions, and we are going to use a lot this theorem. Because the suspicious value of x in a piecewise function are the values where the branches of the function change. And that's why we always will have to check the limit of a function at the suspicious points of the piecewise function. We are going to use the previous theorem now to evaluate limits of piecewise functions. Here is the first example. f(x) is x to the power of 2 plus 1 when x is less than 2, and it is 2x plus 1 when x is greater or equals to 2. And we need to find the limit of the function when x approaches 2, when x approaches 3, and when x approaches 0. Let's start with the first one. To find out if this limit exists, first of all, we have to apply 1, 2, 3. The limit from the right, and when I say the limit from the right, because we are looking at the limit when x approaches 2, you already should realize that when I'm saying the right, I'm talking the limit from the right means the limit of the function when x approaches to 2 from the right. Which is this. We have to use the branch at which the function is 2x plus 1, because 2 plus it's a little bit more than 2. This is just a polynomial, so we can go ahead and substitute. And when we do this, we get 5. 2, in short, we will call it left. It means that I'm now going to evaluate the limit of the function when x approaches to 2 from the left. For this one, I have to use the branch where the function is x to the power of 2 plus 1, because this is the branch for all x's that are less than 2. Here I get 5. In 3, we are asking if those two limits are equal, and the answer is yes, they are. The limit from the right equals to the limit from the left, and the common value is 5. Because the common value is 5, I can summarize and say that the limit of the function f(x) when x approaches 2 equals 5. We like to recall that if you can trace the graph of the function f continuously from one side of c to the other, then the limit of the function x approaches to c equals f of c. This is now important for the other two limits. Now we would like to evaluate the limit of the function when x approaches 3. The suspicious point is x equals 2. Calculus speaking, x equals 2 is very far away from x equals 3. When x equals 3, we are really comfortable in here. It means that we can just substitute 3 in the function. So using the branch for which x is greater or equals to 2, because 3 is greater than 2, we just get that this is f of 3, which is 2 times 3 plus 1 equals 7. The same is true for the limit of the function when x approaches 0. X equals 0, calculus speaking, is not a suspicious point on the function, and it's really far away from the suspicious point, which is x equals 2. So we can just comfortably go and substitute in the function, and f of 0 is 0 to the power of 2 plus 1, and we get 1. Here is another piecewise function, and the suspicious point is again at 2. And we need to try to find out if the limit of the function when x approaches to exist. We're going to apply the 1 to 3 theorem as usual. 1, the limit from the right, we get 5. The limit from the left, we get 1. In 3, we are asking if the limit in 1 and 2 are the same, and the answer is definitely not, because 5 does not equal to 1. We conclude that the limit does not exist when x approaches 2. Example, limit of absolute value of x minus 3 over x minus 3 when x approaches 3. This is a piecewise function, but it's enough just to break down the absolute value of x minus 3. We know that this is itself, where x is more or equals to 3, and we get that. And when it's less than 3, it is the opposite of x minus 3. The limit from the right, x is a little bit more than 3, so we're going to use this. And x minus 3 over x minus 3 is just 1. So the limit of no matter x approaches to what equals 1. From the left, we are replacing the absolute value by negative x minus 3. And we know from algebra that this is negative 1. So the limit of x approaches who cares to what of negative 1 is negative 1. The answer for 3 is definitely no, because 1 does not equal to negative 1. We conclude that the limit does not exist. But I want also to note that if you only need to evaluate only one of the one-sided limits, then each one of them exists.